Hello there. In this video, we are going to learn about converse and contrapositive of a logical statement or uh, conditional statements. Under logic, out of the 5 logical connectives, one of it is implication. In case of implication, 2 statements will be connected by if-then. If the first statement will come and then the second statement will continue. So the if part, okay, this part we call it a premise. The premise, and after then the statement which come we call it a conclusion. So when you are discussing about converse and contrapositive, it's all about the implication part, like P implies Q. What is the converse of P implies Q, and what is the contrapositive of P implies Q? This is, as I said before, it is the same as if P then Q. So let us see the definition. So as you see here with the definition, if a conditional statement P implies Q given to us, we can have converse and contrapositive of it. The converse of P implies Q simply just exchange the place of the premise and the conclusion. Beginning, or considered, we are going to start by P implies Q. So when we say P implies Q, the premise obviously P, and the conclusion, it is Q. But when we are talking about the converse, exchange the place. That's going to be Q implies P directly. It's very simple. For example, if water boils, we can take one statement and we can see the converse of it. For example, let us say if water boils at 100 degrees Celsius, this is a true statement, then let us take any mathematical statement, 2 greater than 3. This is one statement. The premise is water boils at 100, which is true, and the conclusion is 2 greater than 3, which is false statement. Anyways, these 2 statements combined or connected by the logical connective, which is implies. Now, if we try to state the converse of this statement, it's going to be if 2 greater than 3, as it is, I'll take the conclusion will be the premise, then water boils at 100 degrees Celsius. This is a converse. So converse doesn't mean anything. But the 2 statement, the truth value, is that the same? No. Because, for example, as I said before, beginning here, try to observe the original statement. This is original statement, this part. This is original statement. It says what? If water boils at 100 means that is true statement. The premise is true. But the conclusion, 2 greater than 3, false. So in case of implication, like true implies false is true implies false. There is only case which will be false. So that's going to be false. But if you see the converse, 2 greater than 3, which is false, then water boils at 100, which is true. So false implies true, it is true. So that converse and the converse of a given conditional statement, the truth value is not the same as the original. The second part, it is contrapositive. Very interesting part. Contrapositive. What does the contrapositive rule says? Again, our starting point is P implies Q. The premise P and the conclusion Q. Therefore, what's going to be the contrapositive? The rule says, or the definition says, negate each. Negate P and negate Q, and then exchange the place. The negation of Q implies the negation of P will be the contrapositive of P implies Q. So how to state the contrapositive of this statement? Let us try to state it. Okay, when you state our statement, it says, if water boils at 100, then 2 greater than 3. So now we are going to state contrapositive. Contrapositive. So it will be if, I have to say, and then I will negate and bring the conclusion as a premise. It's going to be 2 is less or equal to 3, because the opposite or the negative of greater than will be less than or equal to. Then water boils. Water doesn't boil, because I have to negate it, doesn't boil at 100 degrees. That's going to be the negation of, the contrapositive of the statement. So these are the two topics that we mentioned here. The definitions, contrapositive and converse. Don't forget, for a given conditional statement P implies Q, the converse and its original conditional statement, their truth value is not the same, but the contrapositive will be the same. We will see exercise. So in general, in case of a conditional statement P implies Q, the P we call it premise or hypothesis or sufficient condition for Q. Okay, that is a starter, sufficient condition for Q. What about Q? The Q is said to be the conclusion part, or we call it necessary condition for P. Let us see some examples, especially these two, the contrapositive part. It will help us to prove mathematical statements. So let us see some mathematical statements and let us try to prove. The first statement to be proved, it says, if natural number k is odd, then its square is also odd. As you see here, this statement is a conditional statement. The premise part is, if the natural statement k is odd, then square of it will be odd, it says. So we have premise and conclusion. Now let us consider, okay, in case of conditional statement, to prove whether it's true or false, we need to consider the premise as true, and we have to check for the conclusion. If the conclusion becomes true, that means that statement is valid, or we can say it is a true statement. It's acceptable, proved. But otherwise, if the conclusion part becomes false, by considering or by assuming the premise as true, if the conclusion becomes false, we call it its fallacy or invalid. That means the given conditional statement will be false. Don't forget the rule. True implies false is the only false case. Therefore, under this statement, the premise, if the natural number k is odd, then the square of it is odd, it says. So first of all, we need to accept, or we need to assume the premise is true. So our assumption, or assume, or take as true, k is odd. If k is odd number, we can represent odd numbers by 2n plus 1 or 2n minus 1, or n element of natural number. Any natural number, take odd numbers can be represented by 2n plus 1 or 2m plus 1. Anyways, 2 times some kind of natural number plus 1 or minus 1. But even numbers, in case of this is odd numbers, general representation of odd numbers. But even numbers, no plus 1 or minus 1, simply 2n. Try to record those concepts. Now, if a natural number k is odd, means if k odd, we represent by 2k plus 1. Therefore, let us square, because our objective is to see the square of it. What will happen? That means k square means we are going to square 2 plus 1 the whole square. And this square will be 4n square plus 4n plus 1. How do I do it? Because a plus b the whole square, if you remember from binomial expansion, it's going to be a square plus 2ab plus b square. I just apply this formula, or you can expand actually, but you need to recall this. Then at this point, what I can do, I can group these two together, and I can extract 2 as a common. Only 2. I can extract 4, but better 2. The reason, you will see the next step. It will be 2n squared plus 2n plus 1 remain alone. Now we can represent this whole as m. M, it is 2n squared plus 2n, let's say it. Why? Because m is also always going to be a natural number, because since n is a natural number, if you square it and add with 2n, still it's going to be a natural number. It will be a natural number. Therefore, what it looks like now, this is the same as 2m plus 1. Again, this is the general representation, or the general formula for odd numbers. So k squared, also this is odd. Therefore, our conclusion works. We consider the premise as true, k is odd. We accept the premise as true, which is k is odd, and then we square it. finally, we have got some kind of odd number. This is odd number. This represents odd number. Therefore, this conditional statement is true and it's valid. You can say it's valid or true. Let us see some other example. Okay, the second example here, if a natural number k is even, then its square also even. The same process. What is the premise? K is even. So let us accept k is even. That means k is equal to 2n. You can represent for n element of natural number. Even numbers will be represented by 2 times any variable. 2 times any that variable should be an element of natural number because our domain is natural number. Therefore, k square will be, I'm going to square 2n, it will be 4n squared. And this one, I can write it 2 times 2n squared. Just I take out the 2. Then, again, like that of the previous, let m be 2n squared. You know, m also, it will be an element of natural number. The reason, since n is an element of natural number, 2n squared obviously will be a natural number. Therefore, k squared become 2m. What's m? It is 2n squared, which is an element of natural number. Therefore, this representation, or k squared, represents an even number. This is an even number. This is even. So our conclusion will be the given conditional statement. If this is P implies Q, it's a valid. So P implies Q is true. And it's valid and acceptable, which is a true statement. That means. Let us add one more example. The last example is this: if k is a natural number and k squared even, then k is even. If k squared even, then k is even. This is the converse of the previous statement. The previous statement says if k is even, if k even, then the square also even. So this time, if the square even, the k will be even, it says. That is the converse of the previous statement. But how to prove such kind of statement? The premise here, k square even. This is a premise. And this is going to be the conclusion. That means we can consider. Therefore, to prove this kind of statement, we can apply converse, contrapositive. What does a contrapositive says? P implies Q. It is the same as negation Q implies negation P. I did for this means it's the same as we did for the original one. So we'll try to check the contrapositive. That means we are going to consider the negation of that is true, and then we will see the process. Therefore, what is the premise? Our P this time is k squared is even, and our Q is, it is k is even. So we can prove by contrapositive. Okay, proof by contrapositive. Let's apply contrapositive rule. That means let Q is not even. Let's say, let's take the negative of the conclusion part. Okay, so proof by contradiction. What to do? A negation Q. Let's accept as true. That means let K is not even. Let's say we negate the conclusion part. We took the conclusion part, the negation of the conclusion part. Let us consider as the negation of it. Let us consider as true. So if negation Q is true, and that means K is not even, means K must be odd. If it's not even, necessarily it will be odd. So the square of odd is odd, already you prove here. Previous example, we did it here. Remember, if K is odd, the square of it will be odd. So if K odd, so if K is odd, then K square must be odd. We prove this one already. So we accept K as odd by taking the negation of it. that means the original statement or the premise here is going to be false. It's not even. The negation of it will be true. That means negation P is true. We consider negation Q as true. What happened? Negation P become true. So when you consider Q as odd number, the square of it will be odd. So it contradicts with the original statement. So the assumption fails. So directly the statement is true. Anyways, if you consider the negation of the conclusion part as true, the original premise will not be true, but the negation of it will be true. That means negation of Q implies negation of P become true. This will be true because we consider the premise as the negation of Q as true, and the conclusion which part become true, the negation of P becomes true. True implies true will be true. That means the contrapositive of this statement true means originally contrapositive, and they are equal. So proof by contrapositive means you can consider the conclusion part as true, and when you process, you'll get something which contradicts with the premise of the original statement. Our premise here is what? Remember, what is our premise? Our premise is k square is even. If k square even, then k is even. So we are trying to prove by contrapositive. What do we do? Contrapositive means take the conclusion part as false. That means, or negate it, the negation of the conclusion part as true. Consider like that. So the negation of Q, if it is true, that means k is not even, which will be odd. If k odd, necessarily the square of it will be odd. So the square of k become what? Odd. It contradicts. Contradicts with what? With the original statement. Our original statement, the premise was k square is even. So it contradicts. It doesn't work. So that assumption fails. Our assumption was, it was k is not even. This assumption is wrong. So k must be odd. So that is the way how to prove. Anyways, these are some of the examples that we can use contrapositive and converse to prove statements. And that's the definition. Don't forget to subscribe, like, and comment. Thank you for watching.